Imagine floating in the vastness of space when suddenly a monstrous invisible force grabs hold of you. You're being pulled faster and faster. Light bends, time distorts, and reality begins to fall apart. You're getting sucked into a black hole. But what exactly is happening to you? And how do black holes actually work? Welcome back to the channel. Today, we're diving deep literally into one of the universe's most terrifying and fascinating mysteries, black holes. Buckle up, because we're going to break down the science by taking a hypothetical ride straight into one. Let's explore what happens, step by step, when you're getting pulled into a black hole and what it reveals about the nature of space and time itself. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it. These cosmic beasts form when massive stars run out of fuel and collapse under their own gravity. What's left behind is an invisible trapdoor in space. At the center of a black hole lies the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding it is the event horizon, the point of no return. Once anything crosses this invisible boundary, it's doomed to fall inward forever. But don't picture a black hole as a giant cosmic vacuum cleaner. It doesn't suck everything around it indiscriminately. In fact, if our sun were replaced by a black hole of the same mass, Earth's orbit would remain unchanged. It's only when you get dangerously close that the real madness begins. And that's where our journey starts, at the edge of the event horizon. As we drift closer to the black hole, things begin to feel strange. From a distance, the black hole might appear like a swirling disk of glowing gas and light, an accretion disk spiraling into darkness. This happens because material falling into the black hole gets superheated by friction, emitting intense radiation. Now, as you approach the event horizon, time for you seems normal. But to a distant observer, your descent appears to slow down. This is called time dilation. Thanks to Einstein's general theory of relativity, time near a massive object moves slower compared to areas further away. As you float closer, signals from you to the outside world become more stretched, eventually fading entirely. To everyone else, you appear frozen at the edge, never quite crossing. But for you, you continue falling, and it's a one-way ticket in. No turning back. Now, you've crossed the event horizon. Reality begins to distort in extreme ways. Inside this boundary, space and time switch roles. You can't avoid the singularity because moving forward in time now means moving closer to the center. No amount of rocket fuel or sci-fi technology can stop it. The geometry of space-time inside a black hole is so warped that every possible path leads inward. The laws of physics, as we know them, collapse under the overwhelming gravity. You're no longer just falling through space, you're falling through time, toward a destination no one can escape. Interestingly, you might not even notice the exact moment you cross the event horizon if the black hole is massive enough. It's eerily calm, like floating through empty space, while the universe outside continues unaware of your fate. As you fall deeper, you reach a point where gravity becomes extremely intense, especially near a smaller black hole. This is where spaghettification happens. The gravitational pull on your feet is much stronger than on your head, assuming you're falling feet first, stretching you into a long, thin strand like spaghetti. This gruesome effect is due to what's called tidal forces, and it would tear any object, human or spacecraft, into atoms. In larger black holes, however, the tidal forces at the event horizon are much weaker, so you might survive longer. Still, eventually, the intense gravity will crush you completely. No material, no matter how strong, can withstand the immense compression near the singularity. At this point, everything you are, your atoms, your information, is consumed by the black hole's core. Now here's the big mystery. What happens to the information that made you you? Quantum mechanics tells us that information cannot be destroyed, but black holes seem to erase everything that enters. This creates a paradox that has puzzled scientists for decades. Do black holes store this information? Is it smeared across the event horizon, like a cosmic hard drive? Or does it somehow leak out over time through what's known as Hawking radiation? Stephen Hawking proposed that black holes might emit radiation due to quantum effects near the event horizon, causing them to slowly evaporate. If true, perhaps the information isn't lost forever. Maybe it's encoded in that radiation, just beyond our understanding. This paradox has led to the idea of the holographic principle, that the entire contents of a volume of space can be described by information encoded on its boundary. In other words, maybe you still exist, just in a very different form. One theory that challenges our calm journey into a black hole is the idea of the black hole firewall. This proposes that instead of peacefully drifting past the event horizon, you'd be incinerated instantly by a wall of high-energy particles. This theory arises from attempts to reconcile quantum mechanics and general relativity. It suggests that the event horizon isn't smooth, but rather a burning boundary where information is destroyed violently. That would violate Einstein's principle of equivalence, where free fall should feel like floating in space. So now physicists are debating, is the event horizon smooth and calm, or fiery and fatal? The answer could reshape our understanding of reality itself. Whether it's a firewall or not, this paradox is one of the hottest debates in theoretical physics. In 1974, Stephen Hawking shocked the scientific world by proposing that black holes aren't eternal. Through a process known as Hawking radiation, they slowly lose mass and energy over time. Tiny virtual particles constantly pop in and out of existence near the event horizon. Occasionally, one particle falls in while the other escapes, stealing a bit of the black hole's energy. Over billions of years, this could cause the black hole to evaporate completely. But what does that mean for the information inside? Does it come out with the radiation, or is it gone forever? Hawking radiation offers hope for solving the information paradox, but also introduces new puzzles we still don't understand. Black holes aren't just gravitational monsters. They may also be gateways through time. According to general relativity, if you orbit a black hole closely enough without falling in, time for you would pass far more slowly compared to someone far away. This is known as gravitational time dilation. It's theoretically possible that if you stayed near a black hole for a few hours, years could pass for everyone else. Could we use this to time travel to the future? Maybe. It's one of the few types of time travel that doesn't break any physical laws, yet the extreme conditions make it impractical. Still, it opens up fascinating ideas about how black holes bend not just space, but time itself. Some theories suggest that black holes could be connected to wormholes tunnels through space-time that link two distant points. These hypothetical passages might even connect different universes. If true, falling into a black hole might not mean destruction, but rather a trip through a cosmic shortcut. The idea of Einstein-Rosen bridges, or wormholes, comes from solutions to Einstein's field equations. However, such a wormhole would collapse too quickly to travel through unless you had a way to hold it open using exotic matter. No one's found such matter yet, but wormholes remain a tantalizing concept in theoretical physics and science fiction. Could black holes be creating new universes inside them? Some scientists propose that every black hole might be the seed of a new baby universe. When matter falls into a singularity, it might not be destroyed. It could be reborn in a different space-time. This fits into the idea of a multiverse, a collection of many parallel or bubble universes. If true, our own universe could have formed inside a black hole in some larger parent universe. It's speculative, but it offers a cosmic cycle of death and rebirth, where black holes become creators, not destroyers. Could black holes be creating new universes inside them? Some scientists propose that every black hole might be the seed of a new baby universe. When matter falls into a singularity, it might not be destroyed. It could be reborn in a different space-time. This fits into the idea of a multiverse, a collection of many parallel or bubble universes. If true, our own universe could have formed inside a black hole in some larger parent universe. It's speculative, but it offers a cosmic cycle of death and rebirth where black holes become creators, not destroyers. If black holes pull everything in, white holes theoretically do the opposite, they spew everything out. A white hole would be a region of space where nothing can enter, only escape. Some mathematical models suggest that a white hole could be the reverse time projection of a black hole. But have we ever seen one? Not yet. White holes remain purely hypothetical, and there's no observational evidence they exist. Still, if they do, they might help solve the mystery of what happens to information inside black holes, or even be connected through a wormhole. That would mean what falls into a black hole here could emerge from a white hole somewhere else. At the center of nearly every galaxy lies a supermassive black hole, millions or even billions of times more massive than the Sun. Our own Milky Way houses one called Sagittarius A. These giants shape the structure and fate of entire galaxies. But how did they form so early in the universe's history? That remains an active area of research. Unlike stellar mass black holes, supermassive ones might form through the direct collapse of enormous gas clouds or by merging many smaller black holes. Their sheer mass means their event horizons are vast, large enough that you might not even feel tidal forces as you fall in at first. While black holes themselves are invisible, when they actively consume matter, they light up the universe. These are called quasars, some of the brightest objects ever observed. As matter spirals into the black hole's accretion disk, it heats up to millions of degrees, emitting massive amounts of radiation. Quasars can outshine entire galaxies and be seen across billions of light years. They give us valuable clues about the early universe and how black holes grow. Studying quasars is one of the best ways astronomers can indirectly observe black holes in action. In 2019, the world got its first picture of a black hole. The Event Horizon Telescope, EHT, a global network of radio observatories, captured the shadow of the supermassive black hole in Galaxy Mighty 7. The image showed a glowing ring of gas surrounding a dark center, the event horizon. This was a scientific milestone, confirming decades of theory. Since then, the EHT has continued capturing black hole shadows, including Sagittarius A. While we can't see black holes directly, observing their effects on nearby matter helps us understand their size, spin, and more. Let's get this out of the way. No, Earth won't be swallowed by a black hole. There's no rogue black hole nearby, and even if there were, it would need to come very close to affect us. Remember, black holes don't suck. They attract like any other massive object. If the Sun became a black hole of equal mass, Earth's orbit wouldn't change. The danger only comes if we get too close. So while black holes are terrifying in theory, in practice, they're too far away to be a threat to our solar system. Not all black holes are massive. Some theories suggest the existence of many black holes possibly formed in the early universe, or even at high energies in particle collisions. These hypothetical black holes could be smaller than an atom, but incredibly dense. Physicists at the Large Hadron Collider once wondered if they could create mini black holes in experiments, but don't worry, they'd evaporate instantly due to Hawking radiation. If proven to exist, mini black holes could provide crucial insights into both quantum mechanics and the nature of gravity. When two black holes spiral into each other and merge, they release ripples in space-time called gravitational waves. These were first directly detected in 2015 by the LIGO Observatory. These waves confirm predictions from Einstein's theory of general relativity and allow us to observe black holes in an entirely new way. Since then, dozens of mergers have been detected. Each one teaches us about the mass, spin, and origin of black holes. It's like listening to the universe's heartbeat, each chirp revealing a cosmic collision. Black holes have fascinated not just scientists, but filmmakers and writers too. From Interstellar to Event Horizon, black holes are often used to explore deep existential and philosophical questions. Interstellar even worked with physicist Kip Thorne to visualize a realistic black hole using accurate physics. The film's depiction of time dilation, gravitational lensing, and spaghettification was remarkably accurate. Pop culture doesn't just entertain, it helps spark curiosity and inspires the next generation of astrophysicists to explore the real science behind the fiction. Black holes sit at the crossroads of physics' greatest questions. The future of black hole research could unlock a theory of everything, a framework that unites gravity with quantum mechanics. With new observatories like the James Webb Space Telescope, advanced gravitational wave detectors, and computer simulations, we're on the brink of breakthroughs. Perhaps we'll uncover how black holes shape the cosmos, how they connect to the Big Bang, or how they might be key to understanding the ultimate fate of the universe. Whatever the answers may be, one thing is certain: black holes are far more than cosmic vacuum cleaners. They are gateways to the deepest secrets of the universe. You might imagine a black hole as a kind of celestial body with a solid surface, but that's not the case. Black holes don't have a surface like planets or stars. What they do have is the event horizon, which acts as a one-way boundary in space-time. Anything crossing this boundary is lost forever to the outside universe. But the event horizon itself is not a physical surface. It's a mathematical boundary. If you were falling in, you wouldn't hit anything when crossing it. But interestingly, many physicists now believe that the event horizon might behave like a kind of membrane with quantum properties, possibly storing information or even vibrating. This concept, called the membrane paradigm, gives us a useful way to model black hole behavior, even though what lies beyond remains hidden from our view. It might sound strange, but black holes can be studied using the laws of thermodynamics, the same laws that govern heat engines and refrigerators. In the 1970s, scientists like Jacob Bekenstein and Stephen Hawking proposed that black holes have entropy, a measure of disorder. The more massive a black hole, the more entropy it has. And it even has a temperature, albeit extremely low due to Hawking radiation. This means black holes follow the rules of energy conservation and thermodynamics, just like everything else. This discovery linked black holes to quantum theory and statistical mechanics, offering a rare bridge between seemingly disconnected parts of physics. It's a sign that black holes might not destroy information, but process it in complex, still mysterious ways. One of the greatest unsolved problems in physics is the information paradox. If something falls into a black hole, and the black hole later evaporates through Hawking radiation, where does the information about the original matter go? Quantum mechanics says information can never be lost, but general relativity allows for total destruction. This contradiction is at the heart of modern physics. Some theories suggest that information is stored on the event horizon. Others propose holography, that all information inside the black hole is encoded on its boundary like a 3D object stored in 2D. Resolving this paradox could lead to a unified theory of everything and reshape our understanding of space and time itself. Inspired by black hole thermodynamics, the holographic principle is a revolutionary idea, suggesting that the entire 3D universe can be described by information encoded on a 2D surface. It's like watching a 3D movie on a flat screen, except this screen contains the entire universe. The concept arose from attempts to resolve the information paradox and is supported by string theory. It implies that the contents of a black hole, or even the universe itself, are projections from a lower dimensional reality. If true, our experience of depth, space, and possibly time could be an illusion. It's mind-bending, but offers a possible route to quantum gravity. Black holes are more than just the end states of dead stars. They are cosmic laboratories for testing new physics. Their extreme conditions, gravity, density, energy, push our equations beyond their limits. Studying them may reveal new particles, undiscovered forces, or even a way to unite the Standard Model with general relativity. Some physicists believe that if we can fully understand how black holes process information and emit radiation, we might uncover the fabric of quantum space-time. In this sense, black holes aren't obstacles. They're gateways to deeper truths about the universe, perhaps even answers to what preceded the Big Bang. Yes, they can, but very slowly. Through Hawking radiation, black holes slowly emit particles and lose energy. Over time, trillions upon trillions of years, they can evaporate completely. But this only applies to small or inactive black holes. Supermassive black holes, especially those constantly feeding on matter, grow faster than they shrink. If the universe keeps expanding and cooling, eventually even the biggest black holes might fade away, leaving behind nothing but a faint quantum imprint. This idea adds to the theory of the heat death of the universe, where black holes are the last things to vanish in a cold, dark cosmos. A naked singularity is a theoretical singularity, not hidden behind an event horizon. If one existed, we could directly observe the point where the laws of physics break down. This would be like staring into the engine room of the universe. However, the cosmic censorship conjecture proposed by Roger Penrose suggests nature always hides singularities within event horizons to protect the integrity of space-time. But certain solutions in general relativity hint that naked singularities could arise under special conditions. If they exist, they would revolutionize physics, offering direct insight into the quantum structure of reality.